China just built the world's first certified four-seat electric plane, and the trick behind it sounds almost too simple. A 140 kilowatt electric motor, no combustion, no exhaust, just batteries turning a propeller. The same basic idea as a cordless drill scaled up to aircraft size. The plane weighs 1,260 kilograms at takeoff. You heard that right, about the weight of a small pickup truck, and it just earned the same safety certificate category as a Cessna. And here is the part that blows people's minds. This is not a prototype. It is a commercially certified aircraft, cleared under rules equivalent to America's Part 23. Hit a quick like and subscribe so you don't miss the next one. By the end of this video, you will understand exactly how a 5-year certification process quietly became the real breakthrough. So why has no electric four-seater cleared this bar before? For almost a century, the small piston engine airplane has been one of the quietly perfect machines of modern engineering. Not perfect in the sense of flawless, perfect in the sense of earned. Every part of it exists because it solved a real problem. And it solved that problem so completely that almost nobody thought to question it. Engineers love the piston engine because it is mechanically simple and forgiving of rough, remote airfields. Manufacturers love it because the fuel and parts supply chain predates most pilots flying today. Governments love it because certification standards for these engines were written decades ago and trusted by regulators everywhere. This is not a system anyone stumbled into. It is the result of one of the most conservative, safety-obsessed industries on the planet converging, generation after generation, on one dominant design. So here is the question worth sitting with for a moment. Why didn't anyone solve this sooner? Electric motors have existed for over a century. Batteries have powered cars, scooters, and household tools for decades. Yet the four-seat piston trainer sitting on a runway in Ohio or Guangxi today runs on the same basic combustion principle that powered aircraft in the 1930s. Here is the part most people miss. It was never a lack of imagination. It was a battery problem. Think of it like trying to run a chainsaw all day on the battery from a cordless drill. The motor works fine. The battery simply cannot hold enough energy for its weight to do the job for long enough to matter. That single limitation, energy density measured in watt-hours packed into every kilogram of battery mass, is why a 1960 design still dominates flight schools and short-haul air taxi routes worldwide. It is not stubbornness. It is physics that nobody had yet found a way around. Consider the numbers most pilots take for granted. A typical four-seat piston trainer burns through roughly 40 liters of aviation fuel per hour, about the same volume as 2 full bathtubs drained in a single afternoon of instruction flights. That fuel weighs almost nothing compared to the energy it releases, which is exactly the advantage combustion has always held over batteries. A tank refills in minutes. An engine overhaul, done properly, keeps the same airframe flying safely for well over 2,000 hours between rebuilds. Flight schools built entire business models around that reliability, training pilots on aircraft whose maintenance costs are, by now, almost completely predictable. The system works. The system is trusted. The system is also sitting on top of a problem the industry has quietly lived with for 50 years. Underneath that reliability sits a structural vulnerability the industry rarely says out loud. The small piston aircraft that trains most of the world's pilots runs almost exclusively on leaded aviation gasoline, a fuel formulated in the 1930s and never fully replaced. This is not about convenience. It is about a supply chain built on a substance that regulators in the United States and Europe have spent the last decade trying to phase out entirely, because leaded fuel is one of the last major sources of airborne lead emissions left in modern transportation. Quantify the cost of that dependence and the numbers get uncomfortable fast. A single hour of flight training in a piston aircraft burns fuel that, at current prices, runs a flight school upward of $120, roughly the cost of a full week of groceries for a small household, spent every 60 minutes in the air. Multiply that across a typical flight school's annual training hours, and fuel alone can eat past $200,000 a year before a single mechanic is paid. And in countries without a reliable avgas supply chain, aspiring pilots in entire regions of Southeast Asia, Africa, and Latin America train later, less often, or not at all, not because they lack the aptitude, but because the fuel does not reliably reach them. Here is the detail that puts everything into perspective. This is not primarily an emissions story or a cost story. It is an access story. The countries with the least developed aviation fuel infrastructure are, disproportionately, the countries that most need affordable, scalable pilot training and short-haul air mobility. A fuel-dependent aircraft is, quietly, an infrastructure-dependent aircraft. Every one of those training hours, every one of those maintenance cycles, depends on a supply chain that was never designed with equity in mind. It was designed decades ago for a different world, and the industry kept using it because nothing else had cleared the bar. Two-seat electric trainers had already flown in Europe, proving batteries could lift a light airframe off a runway. But a two-seat demonstrator and a four-seat certified commercial aircraft are not the same problem. One is a proof of concept. The other must survive years of structural and failure mode testing under a regulator's microscope. That left one obvious question hanging over the entire industry. Could a four-seat aircraft actually run on batteries alone and pass the same brutal safety certification as the aircraft it would replace? In 2019, a research team at the Liaoning General Aviation Academy of Shenyang Aerospace University began answering that question with data that was harder to dismiss than anything the field had seen before. Two institutions carried that question forward: the Liaoning General Aviation Academy of Shenyang Aerospace University and its manufacturing partner, Rixion General Aircraft Company, working together in Shenyang, in northeastern China. This was not a startup chasing headlines. It was the same team that had already built and flown a smaller two-seat electric aircraft years earlier, and had spent the intervening years scaling that experience up to something the industry had never certified before. The core idea sounds almost too simple once you hear it. Take a conventional four-seat airframe, strip out the combustion engine and fuel tank, and replace them with a lithium battery pack and an electric motor. That is it. No exotic new flight principle, no radical airframe redesign. Just a different way of storing and delivering energy to a propeller that still spins the same way it always has. Here is what earlier attempts got wrong. Smaller electric aircraft could carry batteries large enough for one or two people because the weight penalty was manageable. Scale that same battery chemistry up to carry 4 people and enough reserve power for a genuine safety margin, and the aircraft becomes too heavy to certify under normal category rules. Think of it like trying to power a full-size delivery van with the battery pack from a golf cart. The motor might turn, but you would never get certified to carry passengers in it. What changed was the battery itself. The team built a 70 kilowatt-hour lithium pack, about the same energy capacity found in a mid-range electric car, paired with an electric propulsion system delivering a maximum output of 140 kilowatts. That is roughly double the horsepower of a typical family sedan, routed entirely into spinning one propeller. Here is the part that matters most. They did not just make the battery bigger. They redesigned the airframe around it, building a lightweight short takeoff and landing structure specifically so the extra battery weight would not eat into the aircraft's usable payload. The airframe itself came in at 1,260 kilograms at maximum takeoff weight, about the weight of a small pickup truck, but built with a 13.5-meter wingspan to keep it stable and efficient at low speed. That wingspan matters more than it sounds. A longer wing generates more lift at slower speeds, which meant the design team could recover some of the weight penalty of the battery pack without needing a larger, heavier motor to compensate. The propeller still turns the same way it always has. Everything underneath it does not. That solved the weight problem. It did not yet answer whether the aircraft could actually perform. Let's start with the number that sounds like a deal breaker. The RX-4E's maximum flight endurance is 1.5 hours, with the manufacturer's stated range of roughly 300 kilometers, or about 186 miles. Compare that to a conventional piston trainer, which can often stay airborne for 4 or 5 hours on a single tank. And the electric aircraft looks, on paper, like it lost the fight before it started. But here is what that number actually means in practice. Most flight training sessions last between 45 minutes and an hour and a half. A student pilot practicing takeoffs, landings, and pattern work rarely needs to stay up longer than that in a single sitting. Most sightseeing flights, the kind that circle a coastline or a mountain range for paying passengers, run 30 to 60 minutes. The RX-4E's endurance ceiling sits almost exactly where the bulk of small aircraft flight hours already happen. The limitation is real. It is also, for the aircraft's primary use cases, close to irrelevant. Picture it like an electric commuter car with a range of only 40 miles, useless for a cross-country road trip, but nearly perfect for the school run and the grocery store, which is what the vehicle was actually built to do. Now here is the part few people expect. Electricity, unlike aviation gasoline, is often the cheapest form of energy available almost anywhere in the world, which means the RX-4E's operating cost per flight hour comes in dramatically lower than a comparable piston aircraft. No fuel deliveries, no leaded gas supply chain, and a fraction of the maintenance complexity of a combustion engine with hundreds of moving parts. It is also close to silent compared to a piston engine, which matters enormously for flight schools operating near residential neighborhoods, and for tourism operators flying low over wildlife reserves or quiet coastlines where noise complaints have grounded routes before. The aircraft cruises at roughly 200 kilometers per hour, and its short takeoff and landing design lets it operate from grass strips and short regional airfields that a heavier, longer piston aircraft would struggle to use safely. That combination, short flights, low noise, low operating cost, and modest runway requirements, points to an application nobody expected. Short-haul medical evacuation in regions with limited road infrastructure, where a fast, quiet, cheap-to-operate aircraft can reach a clinic in 20 minutes instead of a multi-hour drive over unpaved roads. The question was no longer whether an all-electric aircraft worked. The question was who would deploy it first and where. On December 29, 2024, the Civil Aviation Administration of China issued Type Certificate number 0095A to the RX-4E, developed by the Liaoning General Aviation Academy and its manufacturing partner, Rixian General Aircraft Company. Chinese state media confirmed the certification days later, on January 2, 2025, calling it a breakthrough in new energy aviation technology. The field matched the forecast. Field validation matters more than lab results in aviation, because a certificate is not a press release. It is the end result of roughly 5 years of structural load testing, thermal stress testing, battery failure mode analysis, and flight testing, all reviewed line by regulators, whose job is to find the reason an aircraft should not be allowed to carry passengers. The certification process began when CAAC accepted the design application on November 11, 2019. 5 years later, the aircraft had survived every attempt to disqualify it. This certification also mattered because of what came before it. 2-seat electric trainers had already been type certified in Europe in 2020 and in the United Kingdom in 2022, proving regulators could trust an all-electric aircraft with a modest passenger load. But no regulator anywhere had certified a 4-seat electric aircraft under the stricter category that governs the kind of commercial aircraft flight schools and regional operators actually rely on, until the RX-4E cleared that bar first. The design's short takeoff and landing capability lowered a barrier most electric aircraft programs never mention. It does not need a long paved runway to operate, which means it can fly out of the same short regional airstrips already used by conventional light aircraft across Southeast Asia, Africa, and the Middle East, without the operator building new infrastructure first. That detail is publicly recorded in CAAC's own type certification registry, the same open regulatory record any aviation authority in the world can review. This milestone marks a new era for sustainable aviation, paving the way for the commercialization of electric aircraft in the advanced air mobility market. A Volar Air Mobility spokesperson said, following the certification announcement, "If a 5-year certification process surviving structural and battery failure testing surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it." It started with one application, where cost and noise mattered more than range, flight training, and short sightseeing routes. Then it spread outward from there, into medical evacuation routes across regions with limited road infrastructure, and into tourism operators looking for a quieter aircraft over sensitive coastlines and wildlife areas. The claim now had receipts. The response outside China arrived fast, and it arrived as action, not applause. These are not academic citations. These are legal and financial commitments. In September of 2024, months before certification was even finalized, Volar Air Mobility signed an agreement with the United Arab Emirates General Civil Aviation Authority to help establish the country's first green aviation technology hub, aimed at building out clean energy aviation infrastructure across the Gulf region. Volar has since committed to introducing the RX series aircraft globally, with initial commercialization targeted at Southeast Asia before expanding into Africa and the Middle East for private aviation, tourism, and medical evacuation work. Meanwhile, competitors were not standing still. Slovenia's Pipistrel, maker of the two-seat Velis Electro that first proved electric aircraft could be certified at all, continued expanding that aircraft's footprint into flight schools across North America. American developers Beta Technologies and Aviation kept pushing their own electric and hybrid electric designs towards certification, betting that passenger and cargo demand for electric short-haul flight would only grow. Here is the part that puts the pressure in context. China's own civil aviation planners have set a public target of on the order of 100,000 electric vertical takeoff and landing aircraft in operation nationwide by 2030, signaling a regulatory environment actively built to accelerate exactly this kind of adoption. In any market where operating costs for an electric aircraft run meaningfully below a comparable piston aircraft, a real cost advantage is not a trend. It is a competitive pressure no serious operator can afford to ignore. Flight schools operate on thin margins. Regional air mobility operators in developing markets often operate on thinner ones still. A lower cost per flight hour changes who can afford to fly, teach, or expand a fleet at all. For a flight school running a dozen aircraft, that difference can mean the gap between breaking even and closing its doors within a single fiscal year. The full picture of exactly how many patent filings and licensing deals sit behind the specific aircraft's propulsion architecture is not yet publicly documented in detail. That is one figure worth treating with appropriate caution rather than an invented number. What is publicly documented through CAAC's own certification registry is the certificate number, the certification date, and the full technical basis the aircraft was approved against. It is an open data trail any regulator or competitor can independently verify. That combination of public accountability and international momentum was the setup. The obstacles still standing were the real test. If even a modest fraction of the world's roughly 200,000 small piston aircraft were eventually replaced by all-electric equivalents like the RX-4E, the shift would remove a meaningful share of the aviation sector's leaded fuel consumption. a slice of aviation roughly comparable in aircraft count to the entire commercial fleet of a mid-sized national airline. The secondary benefit runs alongside the emissions story. Leaded aviation gasoline is one of the last significant sources of airborne lead in modern transportation, and phasing it out at scale would remove a documented public health exposure risk for communities living near small regional airports, particularly children in neighborhoods close to flight schools. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. First, battery energy density still lags aviation fuel by a wide margin, which caps range at roughly 300 kilometers, fine for training and short hops, but a real ceiling for longer regional routes. Second, charging infrastructure at small regional airfields, especially in the developing markets Volar is targeting, does not yet exist at the scale commercial operation requires. Third, battery performance in cold weather remains a documented engineering challenge, with reduced capacity and range in low temperatures that regulators will scrutinize closely for any expansion beyond China's borders. Fourth, battery replacement costs and life cycle economics over a 10 or 15-year airframe life are not yet proven at scale, since the aircraft has been certified for barely a year. Fifth, no aviation regulator outside China, not the FAA, not the European Union Aviation Safety Agency, has yet certified a 4-seat electric aircraft under their own equivalent standards, meaning international expansion requires an entirely separate certification campaign, from scratch, in every new market, a process that, based on China's own timeline, could easily take another 3 to 5 years per region. Here is the part worth sitting with. None of these challenges change what the certification shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate and access problems it could solve actually demand is a different question entirely. That gap is exactly where the next chapter of this story begins. The story of the world's first certified 4-seat electric plane is ultimately the story of what human civilization can build and where it can build it. For over a century, powered flight has quietly sorted the world into places that could afford aviation infrastructure and places that could not. Leaded fuel supply chains, paved runways, expensive engine maintenance, all of it concentrated flight training and short-haul air access in wealthy regions, while entire countries with genuine aviation potential were priced out by infrastructure they could never quite catch up to building. That is exactly why Volar's stated commercialization path matters. Southeast Asia, first, then Africa, then the Middle East, regions where road infrastructure is often unreliable, where medical evacuation can mean the difference between life and death, and where a quieter, cheaper, electricity-powered aircraft could reach communities that conventional aviation infrastructure has never adequately served. The access gap is real, and it will not close overnight. But for the first time, the aircraft capable of closing it has actually cleared a real regulator's desk. What is genuinely new here, not incrementally better, but categorically different, is a 4-seat aircraft that runs on grid electricity instead of a fuel supply chain, and has survived the same brutal, multi-year certification gauntlet as the aircraft it is built to replace. That is not a minor improvement. It is a different category of solution. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the access and emissions problems it addresses actually demand is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Small aircraft rarely make headlines the way jetliners do, but their numbers compound quietly over decades. One flight school, one regional route, one medical evacuation at a time, multiplied across thousands of airfields the world never watches closely. If a battery pack, rethinking how a four-seat aircraft gets its power, raises a question about how else everyday physical forces might be quietly converted into usable electricity, that story is worth understanding too. And it is the subject of our next video. China just built a bridge that generates electricity from traffic vibration. The link is in the description. If this changed how you think about electric aviation, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you in the comments. Should regulators prioritize certifying electric aircraft for underserved regions first, even if wealthier markets could adopt them faster?